Okay, I will only officially start at 2:05, but in the meantime, just let me blabber because I'm just a bit bored. So today's session, right, I only have 2 hours. So I need you all to know that it will be quite fast-paced. Inevitable. Your school got 1 year to teach you, have 2 hours. But I can promise you these 2 hours will be the most productive 2 hours ever. Okay, there will be some stuff that you will be able to follow. There will be some stuff that you'll find it a bit hard to follow because I'm teaching both the basics as well as a little bit harder. So the harder stuff is natural if you don't get it fully. The good news is that we will most probably upload the recording. Hey, yo, free seating. You're limited to the seats in front. Very good. Yeah, so more or less, today's session, we're covering 6 topics. I have about 10 to 15 minutes per topic. So in today's worksheet, for those online, as well as those here physically, you can start flipping through. It's a mixture of MCQs plus structured. There's a reason why we want to test MCQ stress structured, because for some of the structured questions, the calculations are important. MCQ are only for specific question types to prepare you for it. As I confessed to majority of you just now, the questions are a bit harder. But I'll of course go through in a way that you can understand. So don't be too worried. Okay. Then in terms of break, too bad, I'm not going to give a break. So 2 hours, just suffer with me, but you'll learn a lot. At the end of the 2 hours, if you have questions, you can still check in with me after class. Okay. Let me pass you on the start first. This is the worksheet and the revision kit. We are not really doing a revision kit. The revision kit for you to more or less like study on your own afterwards. Okay. Yeah, let's get started. So my online guys, right, if you have questions, you can type it in the chat, but just be conscious that I cannot answer to everybody's question. Imagine you all ask, 50 of you ask me, cannot be lah, right? So I will answer only those that I think will help to facilitate the learning for everyone. So it will be in parts. So some questions I will answer, some I won't. So if I don't answer you, please don't be too sad. It's just that in the interest of time, I can't answer everybody's question. But I promise that the overall learning was to be there. Okay, so maybe let me just officially start. So today we're doing the Sec 3 pure physics. We have break the physics into 2 parts. So today are the earlier topics, all your kinematics, all the way to work done. Now, just to give you a quick overview, in case none of you have heard of, hey, come in. See. Yeah. So in case none of you have heard of OVERMUGGED before, we are basically a team of tutors. I myself, later I'll do a bit of a self-intro, but we cover everything from O levels to A levels, right? So, I mean, if you guys sign up for these, you probably know us already. So I'm just going to skip this part. Majority of our tutors, you'll bump and see them around. So we have a couple of branches. So right now, where you guys are at is the Serangoon Central branch. We also operate at Bukit Timah, and we recently opened our new center at Parkway itself. So just now I was asking, why do you sign up when your school is all the way there? But maybe you stay near here. On top of that, for those online, if you're wondering where else do we operate in, we are also at Toa Payoh, Jurong East, and Woodlands. So you obviously can choose somewhere that's closer to you if you are thinking of attending classes down the line. All right. Now, we are also looking at Tampines soon. So those of you in Tampines, you're like, wow, okay, possibility. Okay, just a bit more about myself. So I've been teaching for quite a long time. I'm going into my 10th year next year. I suddenly feel very old because like this year, my kids, all of them were Sec 4. Then like I look at their keychain, right? They put a piglet there. So in Chinese zodiac, right, is their sign, right? Zodiac sign. Then I'm also a piglet. Then I realized I'm 12 years apart from them. I'm feeling old, but hey, I still feel like I'm young at heart. So that's for me. So I mainly teach chem and physics. So you're here today for physics. If you pop by the chem session, you might bump into me as well. So for myself, I mean, beyond just teaching, I'm obviously a human as well. So other interests that I have, I used to be very active in floorball. In fact, I'm currently still playing. So I do not know if any of you play floorball, you might bump into me. Actually, I'm a big K-pop fan as well. So I'm definitely more seasoned than you in terms of the K-pop knowledge, but my era is way back. Okay, I don't want to review when, but that's more or less. For myself, I also play a bit of Mobile Legends. If you want to add me, you can play, but I mainly play jungle. Okay, but let's go on to the real stuff. Now, what are we doing today? Now, we need to understand that in the scope of learning intensely within these 2 hours, I cannot cover everything inside your content. That means I cannot go point by point, but I'll tell you exactly what are the key concepts you need to know. So these are the key concepts that will be tested in your end of year. I'll also talk about some misconceptions, especially when it comes to things like vector drawing. Wow, here already scared already, right? Yeah. So I'll tell you what are the 2 ways to draw it. How is it different? Resultant force versus equilibrium. There is a difference. Next, when we tackle questions, I'm not going to focus so much on getting you all to do, but I'll actually show you all how to do it step by step. So the correct presentation in physics, like your formula first, suck in the values, final answer, right? So the presentation is important. Good news is that the answer key is provided. So you all don't have to be too desperate to copy down everything. Listen, all right, and stop the information. So throughout the worksheet, you'll see it's a combination of notes as well as commonly tested questions. Where appropriate, I will put more emphasis on those that will likely come up for your end of year. Okay, but disclaimer, the questions are a little bit more challenging than I think what you'll be used to, but in a good way. So don't say anymore already. Let's just do physics, okay? So these 2 hours will be intense. If we need a break, I see how. But for now, I say because there's no break. But if you need to go toilet, anything, just go. Okay, that one is fine. All right. But the lesson, let's make it as productive as possible. Okay, so I'll get everybody to flip over to the worksheet itself. We'll start with chapter 1. This one you can chill a bit because it's quite easy. But I feel like the questions you might not know how to do. Okay, so we start off with something very basic with SI units. SI units, in other words, is just referring to the simplest unit in measurement. So everything that you see here, the SI unit as well as the symbol, I would say, to be fair to most of you, things like length, mass, time, and even temperature for most of us are quite comfortable. Now, electric current, most of your schools haven't covered it, but it will get a little bit more comfortable next year in upper sec when you do electricity. Amount of substance, does this sound a bit familiar? Where have you all seen this? It's chemistry, right? It's mole, right? But in physics, they don't usually test mole. So it's usually limited to meter, kg, second. The interesting one that I want you all to highlight is actually for temperature. Now, why do I say that? Temperature, normally you take temperature, what's the thermometer reading? It's in degrees Celsius, right? But hey, surprise, the SI unit is actually Kelvin. Kelvin with a capital K. Now, why did I emphasize Kelvin with a capital K? Do you all know what's the difference between a small k and a capital K? Small k is what? It brings me perfectly to what I need to emphasize, which is the prefixes next up. I'll bounce a bit between the curated notes and this. Kilogram, y'all know what's kilo, right? Is small k. So if you're ever going to express, there's a difference between a small k and a big K. Okay, so it's not very significant, but it's something that I want you to take note of. So temperature is not degrees Celsius, it's Kelvin. So these are what we call SI units. All right, moving on. The one that I think we really need to spend some time to discuss is how to draw your scaled vector diagram. Take note that scaled vector diagram is also relevant in your math itself. So the whatever you learn here is applicable for math. Math, on the other hand, has subtraction. So next year, I think in Sec 4, when you learn, it's a bit more complicated. Physics is usually just we add it up. Now, there are 2 scenarios that I need you all to be aware of. Scenario 1 as well as scenario 2. But let me go into a bit more detail. Scenario 1 is when an object is at equilibrium. Now, the word equilibrium implies that the object is no longer moving around. It is just stuck there. In other words, when we consider all the different forces acting on it, the result of it all, it adds up to a 0. That means I can have force 1, 2, 3, right? They fight each other, they cancel each other out. So at the end of the day, you end up with 0. So resultant force 0, FR means force resultant is 0. That is equilibrium. Now, promise me just to remember one thing. If you want to identify something at equilibrium, the forces will interact in such a way where they will form what I like to call the infinite loop. It's not an official thing. This is just the way I like to help my students to remember. Meaning if you continuously follow the arrow, right, it just keeps going forever. So if you see a situation where the forces, right, when you link them up, it just keeps going in this endless loop, or what I like to call the infinite loop, it implies that all the forces will cancel each other out. This is an object at equilibrium. Okay, so this situation means all the forces cancel each other completely. So overall, the result of it all, that means all 3 forces, I add them together, is equals to 0. So this is the situation where an object is at equilibrium. Okay, so RF resultant force equals to 0. I'll say that the good news is that later we'll see this again. Okay, you only have a seat either here or here. You're here for physics, right? Come. Correct. Don't worry. Yeah, so 2 seats left. Make yourself feel comfortable. Worksheet. Oh no, I ran out of worksheet. I'll get you a printed copy later. Ken, don't mind. Okay, I'll print later. Sorry. I'll continue with the lesson first, okay? But you can pass her. Okay, so as I was saying, the first scenario is when resultant force is equals to 0. The one that you'll see a little bit more is what we call vector addition. This one is the one where you would add two vectors together to produce a resultant force. The first scenario, resultant force is 0. There is no resultant force. This one, there is a resultant force. So you take the first one, first force plus the second force, you end up getting your resultant force. Now, for this method, we call it the triangle method. Why? Because we're just forming a triangle. I like to also term it as head to tail, if you can follow me, because this one, the tail goes to the head is biting on the next tail. So you just need to link them up one after another. I like to think of it as from the start point to the end point. From start to end, this itself is your resultant force. Okay, so you can think of it as like A plus B gives you C. So how can questions come out? They will just give you that, oh, there are two forces. Help me find the resultant force. So your goal is to go and arrange them in a way whereby you can form a triangle. From the start to the finish, that is your resultant force. Okay? However, this is not the only way you can do vector addition. The other method is known as the parallelogram method. Why? Because obviously you're forming a parallelogram. So how is this different from this? Actually, the answer that you get is exactly the same. It's just two different ways of getting the same answer. So for the parallelogram method, they both will originate from the same point. Meaning both forces, instead of one after another, they both start at the same point. Using dotted lines afterwards, you would then form the resultant force. Okay, so here, if you notice my blue color arrow is exactly the same as the one this side. These are both the resultant force itself. All good? Now, take note, if you're drawing any forces, you're supposed to draw it with the arrowhead. Then the resultant force is a double arrowhead. That is in terms of presentation. Dotted lines are important because these are what we call construction lines. But you draw them as a solid. Because once the moment you draw solid is like an actual force. Dotted is just construction to help you get to your answer. So in summary, for vector, two things are equilibrium, remember, infinite loop. The forces cancel each other out. Second, vector addition, you can choose either to use triangle or parallelogram. Both will get you the answer. Now, to be completely honest, this is theoretical. When you apply it, it's freaking difficult. You still need to draw the scale and everything. But I normally tell you all not to worry at Sec 3. Why? Because the moment you learn it in math in Sec 4 as well, it gets a lot better. So I think it's important to learn now. But this is not one of those that you panic damn hard if you can't do it. Not yet. But the concepts later are a bit more important. Okay, so what we're going to do next is I'm just going to give you all the next 2 minutes to try out the questions 1, 2, and 3. Give me a bit of time because I want to go and print a worksheet, right? So give me 2 minutes. I'll head out to print a worksheet while you guys try the question. When I come back, let's go through. So coming back at 2:18. Oh, good. Online, you can hear me, yeah? I'm going to start going through the question. So let's take a look at the MCQ questions. I'll bounce over to this side because this side has the answers. So it's a bit easier for me to go through. So answer for question 1 is D. Now, I know your natural question to me will be, Cher, what the hell is candela? You never teach me how I know. Okay, to be honest, candela is just light intensity. But it's okay for me not to teach you that. Why? Because you're supposed to still get the answer even without knowing what candela is. And the reason why I say that is because if you refer back just to your notes, right, which are the SI units? You can tell, right, it is ampere, meter, second, and Kelvin. So just based on that alone, right, you do not need to bother with option A or B. You can still get the answer D. Okay, I think that has to be your mentality. Instead of going to the exams like, wow, I scared. I never see this before. Go and consider the other options first because it's MCQ, right? So it's very realistic for us to expect that you can still identify this 4 as your SI unit without even knowing what candela is. Okay, so that is the way you should be thinking. Next, what's the SI unit for watts? Now, this one is a bit challenging, but let's explore watts first. Anybody even know what is the unit watts is for what? Power, right? So power itself, later we will learn, power is found to be taking work done over time. If you know lah, if you know, work done is force times distance, right? And to break down force even further, F equals to MA, right? That one you should know. So instead of writing F, I'm going to write MA times D over T. Now, what I'm going to do next might be a little confusing, but just follow me through. What is the unit for kg? Unit for mass is kg. Okay, sorry. What's the unit for acceleration? It's ms minus 2. What's the unit for distance? This one can, right? Meters. And the unit for time is seconds. So how do we solve this question when they ask for the SI-based units? It's just basically putting all of the units together. So in other words, it is kg, meter, and there's another meter. Meter times meter. Meter squared. Now, S minus 2 divided by S. Divided by S means, this is more math than physics, but it means that now this becomes S minus 3. So that's actually how you get the final answer for the SI-based unit. You get the main formula first, keep breaking it down until a point where you go like, A, it's all made up of SI units. Lump it all together using a little bit of math to help you to get to the final answer. So this is how it's done. I thought this is a very good exposure. There can be different variations, right? We can test you for example, pressure. What's the base SI unit? You can go and try and work it out. So these are some of the sample questions you are expected to do for measurements. Now, one final one. This one is going back to what we discussed a lot on the vector side of things. I have two forces. The question is asking me for resultant force. Is this equilibrium or is this resultant force? It's resultant force, right? Because here we are producing a resultant force. Now, without even touching anything, just by purely looking at the way F1 and F2 is arranged, can you all tell me which method is better? Do we do triangle here or do we do parallelogram? Triangle, right? Because it's one linked to another. In other words, here and here will give me a resultant force. Remember, right, what I said? From here, start, end. You just need to join a line across, double-headed arrow. This is the resultant force. When do we use a parallelogram? If both forces originate from the same point. That means I got one thought, two things coming out. Then I draw my parallelogram. But for a situation like this, it's more sensible to be using the triangle method, which is quite obviously why the answer here is B. So I emphasize one more time, head to tail, head to tail. All you're trying to do is to complete your triangle. So remember, it's from your start to your finish. Once you connect the start to the finish, that is your resultant force rate. Okay, like I said, if you get it a little bit, good enough already. Because next year you'll get better once you do it in math. All right, so that's for question 3. Your nightmare is here, guys. Okay, to be fair to your kinematics is quite hard. But once again, physics and math is quite closely related. You actually learn a little bit more about this under rate of change in A math. But for now, let's go through what you need to know. Okay, so I'm going to bounce between the notes that you have here as well as my curated notes. Curated notes is like our textbook. So I just have it here as soft copy. I'll be just referencing some of the stuff here. So the first thing I need you to know is that under kinematics, we need to think of it as there's two columns. There's the scalars and then there's the vectors. I believe you guys know what a scalar and vector is. That one is quite easy to understand. So I'm not going to talk about that. Now, on the scalar side of things, which are things that only contains magnitude, is things like distance. Distance means how far you travel. I think no, distance and displacement is not the same thing. Why do I say so? Displacement, I only care about where you start and where you end. Effectively, from where you start to where you end, that is your displacement. Your distance, you can walk very far. Like you see, you can walk like this big loop. But displacement has to be from where you start to where you finish. A direct line with an arrow, because there has a direction to it. So remember, distance and displacement, not the same thing. Say I go on a running track, you know, those in your school, your 400-meter running track, you run one round, what's the distance? 400 meters. But what's your displacement? It's 0. Why? Because you start and end at the same point. All right. So effectively, from start to finish, there is displacement. And there's a direction component to it. So as long as you think about it that way, you will not get confused. Distance is just distance. Displacement, start to finish. Okay. This is really important because it directly affects the next thing we're talking about, which is speed and velocity. Come on, speed you learned since primary school, right? Distance over time, no problem. But what about velocity? It's a bit newer. But velocity is just displacement over time. So like I said, you need to think of it in 2 columns, right? The scalars and the vectors. The one that is probably the hardest for all of us is the term acceleration over here. So acceleration is the change of velocity over time. Now, how can we think about it? Let me just draw it on our the notes here for annotation. You can think about it this way: scalar, vector. The first brother in the scalar is distance. Look at the units, it's just meters. The first member in the vector family is displacement. Unit is meters. I hope you can read. My handwriting not very nice, I admit. So I never complain my student handwriting not nice because my one not nice. Okay, after that is speed. Then velocity. The units, even if you haven't realized, I actually from here, you can go one further, acceleration, ms minus 2. So velocity is the rate of change of displacement. Acceleration is the rate of change of velocity. So you are using one to get the other. So it's like a derived quantity. But I know I say so much, right? You all don't worry yet. Later, when we actually do proper graphical analysis, some of this will be a bit more natural. Okay, I believe this chapter is not about memorizing. There's no really a lot of definition and stuff. Of course, you start with that. But the kind of questions you're expected to do at end of year, or even next year when you take your O-level, are a lot more like I give you a graph, you're supposed to interpret and do calculations, which is exactly the question that I've prepared. Okay, so I know I didn't cover this in a lot of detail, but let me do most of the teaching on the next page. Terminal velocity is important, so I'm going to explain it in the next 2 minutes in a way that you can understand. So what is terminal velocity? I'm sure you all still remember, right? Recently, National Day Parade got red lions, right? Wow, the parachute, everything. So imagine somebody that jumps out of a plane, skydiving. At the start, he will accelerate. Meaning what? When he falls, he will fall faster and faster. But it will reach a point eventually where he's still falling, but he's falling at constant speed. So when you first jump, you will fall very fast. You fall faster and faster until a point where you are falling, but you're just falling at constant speed. That speed can be quite fast, but you are moving at constant speed towards the end. So how does it exactly work? Let's explore it from the forces POV. This is the ball. The ball has a weight of 10 Newton. Meaning how heavy is this? How many kg? 1 kg lah. If you get what I mean, W equals to mg, right? Gravity is 10. Now, in order for this ball to hit terminal velocity under free fall, it will need an equal and opposite amount of air resistance. So air resistance must be 10 newtons as well. This 10 newtons is the weight. The moment they are equal, your weight will cancel out the air resistance. So 10 cancel out. Overall, now it's 0. And if it's 0, what does it mean? It means that there is no resultant force acting on it. The formula that we are all quite comfortable with is F equals to ma. If your resultant force here is 0, mass, whatever value it is, doesn't matter. Your acceleration is 0. Listen up. If acceleration is 0, you are traveling at constant speed. Because you are not accelerating. You're not moving faster. You're just moving at constant speed. So to summarize, what do we need to know about terminal velocity? Terminal velocity will be achieved when the weight and air resistance is equal. You cancel each other out. Your force is 0. When your force is 0, your acceleration is 0. That is the point in which you hit terminal velocity. Okay, so what I'm saying is in this chapter, you need to know the broad structure. You need to know your scalars, your vectors. We will do the graph immediately after this. The only other concept that is very scary for a lot of us is terminal velocity. I will also touch on it a bit later. Okay, but let's take a look at the question we learn alongside one another. There's something that I need to request from you guys, which is try not to memorize this chapter. Understand. At the start, it's more difficult, but once you understand, you will not get this kind of question wrong. So what we are looking at for this question is a velocity time graph. Your velocity is your y-axis, your x-axis is time. Now, for a velocity time graph, we can study it from a few ways. I'll go into it later. We approach the more easy one, part A. Describe the motion of the car from 50 seconds to 90 seconds. Let's take a look. At 50 seconds to 70 seconds, do we all agree that the velocity is decreasing? Right? The velocity, meaning the speed technically with the direction, is dropping from 30 to 0 in the first 20 seconds. So if velocity decreases, is the same thing as saying it's undergoing deceleration. Let that sink in for a moment. My velocity is dropping. That is deceleration. You all confirm know what's accelerate, right? Like go faster, like the car move faster, the sprinter sprint faster. Decelerate is just the reverse law. I'm slowing down. So you know, the moment you see velocity dropping, that is just deceleration. That's all. Okay, so for the first 20 seconds over here, it is undergoing deceleration. 1 mark already. Okay, listen, this is where it gets crazy. From 50 to 70 seconds, is the car moving forward or backwards? Trust me, some of you will say backwards, and backwards is wrong. Wait, chill. Okay, I explain. The reason why you would think it's moving backwards is because you hear the word deceleration, right? Decelerate much a negative one, right? Negative means backwards. No, you can be decelerating and yet moving forward. Give you a very simple example. I'm driving a car, I see a traffic light. I slow down my car, right? Decelerate, but am I still moving forward? Yes. So just because I'm decelerating doesn't mean I'm moving backwards. You get what I mean? So when you decelerate, how do you determine the direction? Let me give you the hack. As long as you are above the x-axis, you are moving forward. The moment you are below the x-axis, that means your velocity is a negative value. You are moving backwards. So I emphasize once more, just because you're undergoing deceleration doesn't necessarily mean you're moving backwards. To study the mode of the vehicle, you can study based on above the x-axis or below the x-axis. That tells you the direction. So in other words, for the first 50 seconds, I'm just moving forward at constant velocity. Then imagine I see a traffic light, right? I slow down as I reach the traffic light, but I am still moving forward. So here the word decelerate uniformly is correct, but we just need to be conscious that the direction is still forward. Not that easy. Okay, but 70 to 80, don't waste time. It just stops there. So it just at rest. That one don't need to explain. Now, what about from 80 to 90? Can you all first tell me what direction is it going now? It's below the x-axis, right? It is moving backwards. And is it increasing from 0 to 20? Yes. So you look at the phrasing, is so damn confusing. Why? Because moving backwards, direction, reverse, right? Below x-axis. And from 0 to 20, the magnitude is increasing. That means I'm moving faster backwards. So it uses the term accelerate uniformly. So imagine this is the motion of the car. Stop. Zoom. Move backwards. But moving backwards faster. So it looks like a very simple question, but if you really want to understand it well, you need to know how to break down the graph. Meaning you need to know above x-axis, what does it mean? Below x-axis, what does it mean? There's still a few more things that we need to learn in terms of breaking down the graph. So I admit this is not easy. You can say opposite direction, no problem. Okay, now, in terms of calculation, the formula that we will all need to know is A is equals to V minus U over T. I think y'all got study a bit, you will know this, right? Anybody know what is V? Initial or final? It's always final minus initial, all right, over time. So V minus U over T from 50 to 70 seconds, my final velocity is 0. My initial was 30. So final minus initial over a duration of 20 seconds. My acceleration is a negative value. It's okay, leave it as negative. Negative 1.5. But you realize what the question is asking for is not acceleration, right? What are they asking for? What's the deceleration? So the moment you go from accelerate to decelerate, the negative sign you just remove. So I'm decelerating by 1.5. Decelerating by 1.5 is the same thing as accelerating by negative 1.5. You're getting accelerate, decelerate, different directions. Okay, so that's how you do A part 2. Okay, next, calculate the total displacement. Now, before you even go into the details of like, wow, so much numbers and stuff, right? Just understand something. Here, I have my y-axis and x-axis. This part your school won't teach one. You'll hear me here. This is y-axis. This is x-axis. What's my y-axis again? Velocity. What's my x-axis? Time. Velocity, time. Now, if I want to find area, area is x times y. You'll get it like this is y, this is x, right? So to find area, it is y times x. Now, or x times y, it's the same thing. So y times x, sorry, I write it as y times x. I think it's a bit easier. What's my y? Y is velocity. What's my x? X is time. Based on formula, what is velocity times time? Displacement. You all know your stupid little triangle with the, you know what I mean, right? The speed, distance, time thingy, right? Distance divided by time is speed lah. So speed times time is distance. This one, I'm just using the word velocity times time. So what I'm trying to impress upon you here is simple. Don't be too concerned with memorizing this. Look at what's your y-axis and what's your x-axis. Your y-axis is velocity. Your x-axis is time. So when you take y times x, velocity times time, it gives you your displacement. So what we are looking at here is that the area underneath the graph represents your displacement. I repeat one more time. Area underneath the graph is your displacement. Above the x-axis is displacement in the forward direction. Underneath the graph, the area is the displacement in the negative direction. So if I can just use the highlight to be a little clearer, this entire area here of this trapezium, this entire area here, this is the displacement in the forward direction. I'm not doing the math part on how to calculate the area. That one is fine. But I need to impress upon you that this is displacement. And displacement in the forward direction. Over here, this cute little triangle. This cute little triangle is below the x-axis. So which direction is it moving? It's moving backwards. So this area over here is the distance move in the negative direction. So same thing, this is displacement, but now the direction is backwards. So displacement backwards. So to find the total displacement, you take forward minus backwards. That's all. So what are the analyses? Let's keep in mind. Above x-axis, forward. Below x-axis, backwards. Area underneath the graph for a velocity time graph gives you the displacement. You have forward displacement. You have negative displacement as well. That means backwards. Bonus question. Come, thinking students. How to find total distance? Green plus blue. You get it? Because distance, do I care about the direction? I don't care. You move forward, backward is still distance. So I can take the green area plus the blue area. That's total distance. But is it the same thing as total displacement? No, right? Displacement, I care about the direction. So if I move forward by this amount, and then I move backward by this amount, I do a subtraction. And once I subtract, I'll get the total displacement. Okay, so that's for part B. Lastly, let's go on to part C. Sketch the displacement time graph. What was given is a velocity time graph. What you have over here in part C is the displacement time graph. Obviously not the same thing. So what you're supposed to do is to sketch out how the displacement changes over time. Now, the first part, this one is easy. And the reason why I say that is in the first 50 seconds, we're just moving at constant velocity, right? So if you went to calculate the area underneath the graph, from this to the first 50 seconds, this area here is this area here. And 30 times 50, 1,500. I think this one just a straight line. Constant velocity. Very simple. But I think the headache comes now, right? 50 to 70, what jialat. Why is it curve? Okay, slowly. I'll teach you another thing. Listen up. Displacement time. I'm going to go back to the same explanation that I did just now. Y and X. People, how do we find gradient? Gradient is equals to Y over X, right? What's my Y? Displacement. What's my X? Time. Come, big brain energy. Displacement over time, what is it? It's velocity, right? So what am I trying to tell you here? For a displacement time graph, what does the gradient give you? The gradient gives you the velocity. Why is this so important? From 50 to 70 seconds, you go back and look at your graph again. From 50 to 70, we all agree, right? 50 to 70, what's happening to the velocity? The velocity is decreasing. From 50 to 70, velocity is decreasing. Velocity is the gradient. Therefore, when I draw the graph, if I were to sketch out a tangent to study how the gradient is changing, my gradient should be decreasing. Because if velocity is decreasing, my gradient should be decreasing. Which is why this part is a curve. At rest, no need to say, it just stops moving. So the hardest part about part C is really understanding why there's a curve. There's a curve because your gradient here is your velocity. And if velocity is decreasing, your gradient is decreasing, you should be getting a curve that's getting gentler. I know not easy, I already warned you already, okay? But absorb what you can. All right, when you go back and look at this again, it will start to make a bit more sense. Okay, so to finish up the key learnings for this question overall, understand above x-axis, below x-axis, forward, backward. Understand that you can take y times x, area underneath the graph to find displacement. And when you're studying what the gradient represents, you can look at what is y over x. Displacement over time represents velocity. So the gradient is the velocity. We try one more. If this one, we go back up. What does the gradient of a velocity time graph give you? Y over x, velocity over time. Gradient represents acceleration. I'm giving you all the broad strokes of how to master this chapter. Cannot be you do one question, you expect your end of year exam get A1. No lah, not so easy. But at least the thinking process here is important. Because I think a lot of schools, they just go and They don't help you to really understand how to break it down. So it's not easy. It is one of the harder chapters for sure. But when you're doing practices, I want you to don't blindly just some formula and do. I always tell all my students, if you want to get a B3, memorize all the formulas, all the definitions, you can get a B3, no problem. But if you want to get an A1 in physics, you need to understand the concept. So you cannot do so by memorizing the formula. Memorizing formula is the start, but it's not the end. Okay, so you have to make it a point to tell yourself that, okay, I need to understand why is it like that. All right, so in this case, the analysis comes with the gradient, area underneath the graph, above, below the x-axis. Okay, got to move on. Dynamics. I got a question for you all. Do you need to memorize Newton's first, second, third law, the definition? Your teacher got say need memorize. Your teacher bodoh, don't need. Okay, to be very clear, you only need to learn how to apply it. But your teacher might get you to memorize because they want you to at the start, learn properly what it actually is. But the truth is that they won't test you define Newton's law. It's not supposed to be like that. They ask you to apply Newton's first law to a particular situation. How does it work, right? So that is how it should be, not a blindly copy-paste in terms of definition. So there are 3 Newton's law in total. These are the more summarized version of it. Newton's first law simply means if an object is not moving, it will move. If an object is moving already, it will continue moving. The key terminology we associate with Newton's first law is the word inertia. If you don't get inertia, just think of this: momentum. Momentum, very easy to remember. So I always use the word momentum. If you know, for example, when Usain Bolt sprints past the finish line, does he immediately just stop? Because it runs so fast, right? He says stop. No, the momentum will bring him through, right? So some of you that play sports, when you're sprinting, you cannot suddenly stop as well. There's a bit of momentum. So that is inertia. Because you're already in motion, you want to continue in motion. But let's say you're just sitting here, right? Like a Buddha, you don't want to move. Is it easy to get you to start moving? Very hard. So if you're at rest, you want to remain at rest. My best example is this. Have you started revising during this September holiday? For heaven, right? So haven't studying, right? Very hard to get the momentum going on, right? It's the same thing as in the morning, your mother wake you up, you don't want to move, what? That is inertia, right? But once you're moving already, when you wake up, you get moving, you keep moving. So it's very important to build the momentum. All right, so inertia and momentum, same thing. You don't move, you don't want to move. Once you start moving, you continue moving. That's all. So don't overcomplicate inertia. Second law, you're confirmed know. What's the famous formula? F equals to M. But let me make a life-changing difference for you right now. It's not F equals to MA. Remember this, remember my face when I say this, it's RF equals to MA. Freaking important. RF stands for resultant force. If you memorize formula, you will memorize F equals to MA. Then you get a question, wow, so easy, force mass acceleration. Answer wrong. Why? Because it's never about the force. It's the resultant force. Now, in case you do not know the difference between force and resultant force, there can be multiple forces acting on one object, 2 to 3. The result of it all, that means this one minus this one plus this one, you add it all up, that is your resultant force. So it is that resultant force that equals to mass times acceleration, not just force. Let me give you all a question that I think can really help. Okay, if you look at this question and you blur, you only memorize formula. You never come for our revision session, you'll be like, hey, F equals to MA, bro. You think so easy, right? But you look at the numbers, it doesn't make sense. Why? Imagine I put in my force, okay, 24, right? Equals to MA, my mass is 6 kg. I accelerate at 2. The math is not mathing, guys. 6 times 2 is 12, it's not 24. Then you'll be like, huh? How do this question? Give up. Wrong. Confirm. So that's what happens when you memorize formula F equals to MA. But remember, RF equals to MA. Now, I'm going to use this commonly tested question to explain a bit further. For a box with mass, okay, this is wrong, so please don't copy this and write this down as the working element. Okay, so I like to draw a diagram so it's a bit easier to visualize. So right here, we have a box. Okay, why did I draw so high? Let me draw a bit lower. Like that. So the box is 6 kg. The acceleration is 2 meters per second. A force of 24 newtons is being applied. However, we cannot just say that the 24 newton is the only force acting on the object. I need you all to have the awareness that if you're pushing a box on the floor, it will experience friction. So there is a friction. Now, why is RF so important? RF is accounting for all the forces acting on the object. Now, what do I mean? RF here, in this case, as you can see, is your forward pulling force of 24 newton. So let's just call it driving force. That means what is pushing it forward? Minus friction. My driving force forward is 24 newton. my resultant force, RF equals to MA, 6 kg times 2 ms minus 2. My resultant force is only 12 Newton. Okay, the math is gonna materialize, don't worry. My last question, how much is friction? My forward is 24, but at the end of the day, the resultant force is only 12. So how much friction are we talking about? It's 12. So my friction here, what I'm calculating that friction needs to be 12 Newton. So that my forward minus the friction in the opposite direction, 24 minus 12, my overall resultant force is 12 Newton. So the question is not that simple. It's not just F equals to MA. Resultant force means forward minus backwards. Forward 24, backwards 12. Result 12. So that 12 equals to MA, mass times acceleration. Have we solved the question yet? No, I was like, wow, my God, so long. But now you know the friction, so life is great. Now, if my acceleration is now 4, how do we solve the question? RF equals to MA. My acceleration is now 4. My mass is the same, it's still 6. So I know that at the end of the day, my resultant force should be 24 Newton. So resultant force equals to driving force minus friction. My resultant force is 24. My friction stays constant at 12 Newton. So final one, what is my new driving force? Driving force minus friction gives me my resultant. So how much is my driving force here? It has to be 36. So 36 minus 12, forward minus backwards, my resultant force, 24 Newton. So the force applied to the box is 36. Trust me, you don't come here today, you won't know how to solve this in your confirm. It's F equals to 8, so no, it's not that. Okay, so the main learning point here is that it's resultant force. You need to account for the forward force and the resistive force. If I flip it from sideways to up and down, do you all know what are usually the two forces in play? There's weight and air resistance. You take weight minus air resistance, that's resultant force. To hit terminal velocity, your weight and air resistance must be equal. Then they cancel each other out. Your resultant force is 0, acceleration 0. Can I get it? Not right, okay? But just remember this, it's never F equals to MA. If there's anything you learn today, RF, resultant force. Okay, follow that religiously and you'll protect yourself in that exam. Okay, now, this one is a bit more difficult. So I'm going to guide you through in terms of the thought process. The question still follows a similar concept. But the good news is that this is a frictionless. So we don't have to account for friction. There's no that resultant force anymore. If you have a highlighter, highlight alongside me. 16 Newton is in charge of pulling both R and S. Oh my God, wait. You get it? So the 16 Newton, I'm pulling both R and S. So when we are doing our calculation, we can very comfortably say that RF equals to MA. It is 16 Newton. My total mass is 6 kg plus 2 kg. Okay, sorry, I'm just going to quick math this a bit. 2. So the whole thing is accelerating at 2. Now, what they want is they want to specifically isolate and find out how much force is being applied to just this rope alone. Right, what is the tension here? This one here is solely in charge of pulling R. It doesn't have to pull S. 16 had to pull both R and S. This one is only pulling R alone. So R alone is 6 kg. What was the acceleration? It is 2, right? So to solve for the tension, aka your resultant force, is equals to mass times acceleration. You're only pulling the 6 kg box, and the 6 kg box is accelerating by 2 meters per second squared. So 12 Newton. Yeah, go and turn down the aircon, a bit hot. I'm very passionate about it. If you're getting sleepy, you can go and snack. Stay awake fast. But halfway through the battle. Okay, so these two questions, the reason why I went through them is not because I genuinely think if I don't go through, you won't know how to do. That's why I wanted to go through these questions. The easy ones there are, but I think those you'll do in your workbook and stuff already. So I'm really emphasizing on the things that your school will not pick up. Now, this is is never as simple as it seems. Now, this one, let's go through it together. I'll just give you all 1 minute to read through question, all of it, then we'll talk about it together. Friction depends on the surfaces. Yeah, I just reposted the links to download the worksheets in the chat. So please go and download if you need to. Okay, let's discuss, because the truth is that we haven't really discussed Newton's third law, right? We talk about Newton's first law, inertial momentum. Second law, RF equals to MA, right? That one you can kind of internalize. But what about Newton's third law, right? We haven't talked about it. Newton's third law, if we look at the official definition, read the official definition. The truth is, you probably don't know what that means. So let's see. Newton's third law states that for every action, there's an equal and opposite reaction. If body A exerts a force on body B will exert an equal and opposite force on body A. What? Okay, this means, right, that when you push somebody, that person is also pushing you. When I'm pushing against this wall, right, as much as I'm exerting a force on the wall is actually pushing me back as well. Okay, so action-reaction pair just means that when, you go and watch movie doing the Rock Johnson, he always headbutt people, right? With his head. Then it's like, you think it's a good move? I think it doesn't make sense in physics. Why? Because when you use your head to smash into other people's head, the force that the person is exerting on him is the same. It just looks cool. It doesn't work in a real fight, guys. So please don't go and headbutt other people. Okay? Because when you headbutt other people, you are hurting them. Doesn't make sense. Okay? Now, for some of you, I do not know whether you have this friend in school, right? Okay, I was from a boys' school, so a bit chaotic. I was just chilling. I just legit not doing anything. Somebody will run up to me from the back, right? Then just slap my back. I do not know whether you have that friend in school. Somebody will just slap my back. But do you realize that when the person do that, you will hurt, right? Because he slapped you. But actually, his hand also pain. When you give somebody a high five, you high five too hard, is that person pain, you also pain. Why? Because it's equal and opposite. The forces are always on each other. So that is just Newton's third law. I push you, you push me. I slap you, you slap me. So technically, when I punch somebody, not that I encourage violence, when you punch somebody, actually the person's face is hitting your hand as well. So you always feel an impact. Okay, so that's what we mean by equal and opposite. All right, so that's Newton's third law. But Newton's third law in theory sounds okay. Like, sure, I get it, Newton's third law, sure. But when we put it into practice, that is when it gets a little more complicated. Now, there is something here that I want to highlight. This one, very common misconception. Action-reaction pair. I tell you what the misconception is first, then I tell you what's the correct answer. Okay? So most of you will be thinking about it this week. My helicopter, y'all don't laugh. I try my best to draw helicopter. Let's just say when I was in primary school, my art teacher wasn't very kind to me. I do not have much confidence. However, it's not bad, guys. It's not bad. Okay, just humor me a little. Okay, so the helicopter, the rotor will spin, right? So the rotor would produce an upward force, right? So like that, upward force. Then most of us will also agree that the helicopter got mass, right? So the helicopter will also have weight. And these two can cancel each other out. So for a lot of us, at first glance, we'll go like, hey, this is an action reaction thing. But it's not. But it's not. Get it? But it's not. So like, what? Right. So it's equal and opposite, right? Equal in value, opposite in direction. So why is it not an action reaction pair? It's because on top of those two criteria, there's another two more criteria. So I go back to the notes a bit. If you want to write this down, it's also in your notes, just maybe not in point form. Other than being equal and opposite in direction, they must act on different bodies and be the same type of force. Same type of force is a bit too complicated. I don't think I want to go through it today. But act on different bodies, this is important. Let me show you. The keyword here is A on B, B on A. The term here is action, reaction, pair. The underrated word is the word pair. One pair got how many? Two people. Okay, so you can only evolve two people. Now, why do I say my previous example with the propeller and the weight is not an action-reaction pair? Let me debunk it for you now. It's going to be a bit complicated, so follow me through. So when we go back to this example, the upward force, who is evolved? There's the propeller. That means the blade, the thing that's turning, right? And what is pushing down on is air. When the propeller push the air down, the helicopter go up. So what's the pairing here? Between the helicopter / propeller with air. So this is the two pairing, propeller push on air. But when we use the word weight, who is the pairing? The pairing for weight is actually between the helicopter / propeller, same thing, with Earth. Why Earth? Because Earth has gravity. So this is why the pairing is wrong now. One is with helicopter and the air. The other one is helicopter and Earth. So the weight and the propeller is not a pair. This is a trio already. Then your question might be, what is the pairing? If my propeller exerts a force on air, it is the air that's exerting a force on the propeller. Very simple, don't overcomplicate. A on B, B on A. Propeller on air, what's the pairing? Air on propeller, full stop. You could name another action-reaction pair, right? Propeller on Earth, Earth on propeller. That's a simplified one. I know I'm not going into very big detail, but it will be in by your end of here. So when we're talking about action-reaction pair, it is not the helicopter propeller and the weight. These two are not an action-reaction pair. The action-reaction pair with the propeller is air pushing on helicopter, then the helicopter pushing on air. So air on helicopter, helicopter on air. I know it doesn't fully make sense, and I wish I can spend the next 1 hour going a deep dive, but given the nature of this revision session, I'm going to limit it to this. So your main takeaway for Newton's third law, when I say pair, it has to be a pair. A on B, B on A. So just because they are equal and opposite doesn't necessitate that it's a pairing. It has to be only two parties involved. The propeller push the air down, air push the propeller up. That's why the helicopter go up. So you all know for a boat, the engine, right? The engine push the water backwards. The water will push the boat forward. You get what I mean? So that's how it moves, right? So same for the helicopter. My helicopter, the blade turn, right? Push the air down. The air will push the helicopter up. That's why the helicopter goes up. So there's no weight involved. Yes, there's a weight we need to cancel out, but air resistance, weight, this kind of thing, yes, those are all forces, but it's not a pairing. This is one of the most difficult things to understand. I bet your school didn't teach this, right? But this tested, yes, it's obviously tested, right? It even appeared in 2014 TYS. It's about book one. I mean, if I got time, I can show you. Okay, let me show you real quick. It's like here. This one. So this is a O-level question. Action, reaction, pair. So you can do focus on book on table, table on book. The one that I was talking about, like A on B, B on A. So this one you need more time to digest, but you have to be aware of this. Because a lot of this, if I don't tell you, I don't think you will know. Okay, to deeply understand it, we will need a bit more time. There's no running away, right? We will need that kind of repetition when you do your practices. But at least now you know that this is a thing. So that's why I tell you, you memorize formula and get A1, man, cannot. These are the kind of things that you need to know. Okay, so that is for part A. Even though it's 1 mark, but freaking hard to get this 1 mark. Okay, for the remaining, I will not spend too long. Okay, reason is simple. RF equals to MA, like bruh, sure, I can do it, no problem. Weight W equals to mg, also okay. Finally, how does the word resultant force work? We need to take all the forces acting on it, right? So naturally, what we'll do is we need to use the answers from the previous part to solve. So resultant force is the lift. In case you're wondering, lift is upwards. This is the same one that the air pushed on the helicopter. That's the same thing. Then weight is downwards. So we can do a subtraction to get the resultant force. The rest is honestly just math. So I will not spend too long worrying about it. So you get it, how the question will work. So the chapter on dynamics can float around any of the 3 Newton's law. But like I said, you don't have to memorize the law. It's about the application of it. Because MOE wants thinking students. They don't want you to just vegetate and memorize. Yeah. No. They don't want that. They want you to apply. Yeah. So your life is now harder. Okay. In a perfect sense, we have a very tiny part in part D because I wanted to make sure that we had a chance to talk about terminal velocity. So I'm going to give you all the next minute to really look through, take down the keywords. When the skydiver falls, air resistance increases. Remember this one, we said weight and air resistance, same. The moment that happens, they cancel each other out. Keyword, no resultant force. No acceleration. In case you blur, let me just write down the formula for you. So when your resultant force is 0, your acceleration is 0. That is terminal velocity. Oh, David, the other one is the curated notes. That one is paid, so it's not free. But you can order it online. If you join tuition, you get it for free, something like that. It's basically our textbook. I like to call it the Bible. When you guess who wrote the Bible? It's me. Okay, but it's really, I find it's really good because it has the content part. But whatever you have here is good enough. Don't worry. You can use it for your end of year. You will survive. I screw up the printing for my JC. JC, the QR code, right? Supposed to link to the page. Then when it's scanned, it's the Sec2 page. But I was the one that made the mistake. Oops. But your one, no mistake. Your one should be fine. In those online, if you want to get a copy of the A5 revision kit, you can drop by any of the branches to self-collect. Okay, so we did print extra copies. So you just head down to any of the branches closest to you, you can go and collect. Not just for physics, you can collect for the other subjects as well. So it's like you just come in, you take what you take. You don't take everything now, of course. Okay, you take what you need, then that's fine. You leave some for the rest that are collecting too. Okay, don't worry, because the answer key is provided. So I think what's more important is that as you are doing, you need to start to think and make sure some of this is absorbing. Okay, I'll be lying to you to say that this is easy. No, it's not. But need to know. I'll say that that's just the key thing. Okay, I'll move on. You all still cannot. Maybe a 1 minute break. Anybody want to eat some snack? You can open up now. We bought Hello Panda. Even got seaweed. Okay, I love the seaweed. Okay, but we chill a bit first. Give your brain 1 minute to rest. Okay, then we'll start. 3 more chapters. Yeah. So toilet, I think there's you walk out, you turn right. There's a toilet. Okay. Hey, go toilet, don't need ask me. I'm not your school teacher, just go. It's fine. But you know where to find it? Go out, turn left or right, both got toilet. So are you all attending any other revision sessions? Which ones are you going for? Math, English, bio, chem. Which ones? Okay. For the goodie bag, technically you can collect one more. But if you find like I don't need like 3 of the same tote bag, you can take the loot inside lah. Then you leave the bag here lah. If your collection, I'm not gonna stop you, but you take the stuff inside camp, but you just leave the tote bag here. Then maybe you can give somebody else that wants it. Because I think it's really cute. But like, yeah, but I was just telling them my girlfriend designed it. So it's like, hey. Okay. We give it a bit more time for either of them to come back from the toilet, then we start. The next chapter is moments. One of the more confusing one. Turning effect. Oh my god. Okay, let's talk about it in a bit. I see a lot of you actually come by yourself. Why you don't want to ask like a friend to sign up? Is it no more slots? You know, fast fingers. Okay lah, shall we just do this? Moments, pressure, who energy power. And done. Okay, let's start on moments first. You realize, right, that I didn't bother with the formula because you know that's not my thing now. Memorizing the formula, you go and memorize on your own. Of course, you do need to know that moments is force times perpendicular distance, but doing the question is more important. Now, the one where we actually need to talk about concept-wise a lot more is equilibrium. There are 3 types of equilibrium you need to know: stable, unstable, neutral. Now, stable, what does it mean? Stable means if I tilt it a bit, it goes back to the original. Stable. It doesn't topple. So tilt a bit, go back. Unstable means if I tilt it and I let go, it will drop. This is unstable. So you don't have to think too hard. Stable means go back. Unstable means topple. That's all. Now, the hardest one to understand is neutral. This bottle is actually a good neutral because when I roll the bottle, it will just stay at its new position. That is neutral equilibrium, meaning it doesn't really topple, it just stays at its new position. A very easy one, soccer ball. I kick the soccer ball, it roll, it stops somewhere. That's neutral equilibrium. Why? Because the ball cannot topple. It just stays at its new position. One of the key criteria is that the center of gravity to the base, this area, the length here is always the same. Imagine I keep rolling it, it's still the same height above the ground. Same for a ball. So that is how we think of a neutral equilibrium. Okay, let me quiz you all a little bit. Show you an example. I like this one a lot. A, B, C, D. If I push A, would it topple? Would it drop? Yes, unstable. B, if I move it a bit, will it drop? Yes, unstable. C, if I move it to the side a bit, what will happen? It moves back, right? Stable. D, if I move it a bit, it would stay at its new position. Neutral. Not that hard, right? Yeah. So stable, unstable, neutral. Now, however, there is a specific way to explain it in a structured question. So later I'll talk about that. But you of course need to understand the difference between the 3 first. Okay, so let's go back in and take a look at some of the questions that will be coming. This is the answering technique. This is literally how you should be writing an exam. Okay, I personally hate that it has to be very structured, but in an exam, if you want to score, it has to be written in a specific way. Keywords, all right? Later, we'll talk a little bit more about this. Now, factors affecting stability. There's only two: center of gravity and base area. The lower the center of gravity, the better. The wider the base area, the better. So you watch F1. I don't know whether you watch. I don't like it. I just think they're noisy. Okay, the car is all very low center of gravity. The base area is wide, so the car doesn't like flip or anything, right? So it's very stable. You get what I mean? Do you know when you take a double-decker bus, you're not allowed to stand on the second level? Why? It's like no space, squeeze a bit, go upper deck, stand there, cannot. Why? Because if the bus suddenly need to make a sharp turn with too many people on top and very little people below, what happens to your center of gravity? It's higher. The whole bus is less stable. Doesn't work that way. So you all go to Genting, you take bus. Where do they store the luggages? It's usually below, because they always want to make it bottom heavy. The top cannot be heavy. Top heavy, it might collapse. You get what I mean? So you're not allowed to stand on the second level of a double-decker because that would increase the mass distribution on top, making the center of gravity go higher. So that cannot work that way. Okay? So there's a certain reason for it. I don't go like, uncle got space, can squeeze on top, cannot. Okay? That's for the safety of everyone. Okay, now let's take a look at some questions. The first question, this one, the reason why we include this question is to really deepen your understanding of the word perpendicular distance. Now, what exactly is perpendicular distance? A lot of you are super duper comfortable if I draw the diagram like that. Like, hey, this is fine, I get it. Pivot to perpendicular distance. Easy, no problem. I think it's fine. This one, I'm not worried. You look at it 1 minute, you get what I mean. Perpendicular distance to the pivot. But the problem comes when it's like, oh shit. Where is my perpendicular distance? You start to panic. Okay, so there is a very definite way we can approach this to make life easier. I would suggest you have a ruler and a pencil. So if you have it, take out. You don't have whatever, but I'm going to draw it for you. So this is how I like to teach my own students to do it. I have this. I will extend this line. My line not very straight. Yours should be straight. Okay, I'll try again. So I'll take a pencil. I have my force, right? Small QQ arrow. I want a long one. I make it as long as I can. Then I'll take my ruler and I'll slide it up and down. Okay, let me show you what I mean. This one's a bit hard to visualize unless I do it. Those online are a bit hard to see. Can I borrow a ruler? There's a quick one. Yeah, so for those of you here, this one, what I do is, this is the pivot, right? I just slide it up. But this is my perpendicular. Okay, or you can follow the arrow, the arrow going down, like here to here, perpendicular distance. So that's why I like to extend the line of action of the force, because it helps me locate the perpendicular distance more easily. So for my online gang, right, the perpendicular distance I'm referring to is here. You get what I mean? So the difficult one is always when it's at an angle, like slanted a bit. But to solve it all, just extend the line. Use your ruler to trace until where it touches the pivot. That is your perpendicular distance. I'll say that for A is quite easy. Because A, like, everything is straight. Like, we're not dumb, right? We can do this, like that. We can even do for this one, right? We do this. I hope you are starting to get a hang of what I'm doing. The typical perpendicular distance, I don't care. That one, you are fine. This is where it's difficult. So I'm really trying to do more of the value add part. Okay, things that basic stuff, you already know I expect a certain level. This is the more difficult part. Now, the one that I will say is the most confusing, which is also the answer, is D. The force extends this way. Can anybody tell me how much is the perpendicular distance? 0. You get it? I cannot draw any blue line. What? So if F times 0, what's my moment generated? 0. So which one is the least? In fact, it's not even least, it's 0. Answer is D. If I compare A, B, and C, which one gives me the most moment? A, because A has the longest perpendicular distance. B and C got a bit, but not as much. So basically, when you're pedaling a bicycle, the point at which you exert the most moment is when your pedal is at this position. You know what I mean? Then here's a bit less. 0, less, maximum. So if you want to accelerate off your bicycle, the best position is about here. Then you push, then your thing move forward a lot. So this is technically the same thing as a bicycle. And any of you like cycling? I cannot, my bike get too pain too fast. I really don't get cycling. Okay, this one, right? Question 2. Your choice. You want me to go through? It's freaking hard. Anybody want me to go through? Okay, I go through. If you don't get it, don't kill yourself. Do you all know which school this is from? Do you all know what's NYGH? Nanyang girls. They're a bit crazy, right? We got our IP classes, so we pull this out for fun. But if you don't get it, it's okay. I'm still going to explain. Hopefully, you can follow. Now, the reason why I say question 2 is a bit insane, right? It's because there's no freaking pivot. So, no pivot. Okay, so the pivot, right, usually in such a scenario, we will let it be either F1 or F2. I repeat again, if there is no pivot, the pivot is not in the middle. The pivot is either at either point of the forces. So what do I mean? So let's try this first. Let's imagine there's a force pushing up here. Let's use this as the pivot. We were told as well that this is 2 kg. Don't use 2 kg. 2 kg is 20 Newton. Uniform rod, 8 meters. So I have my weight of 20 Newton in the middle. So the distance from here to here is 2 meters. The distance of F2 to here is how much? 5 meters. It's just math, okay? So you just take me at face value. This is 5 meters. So how do we solve this question? Okay, this is where it gets a bit tricky. This weight to the pivot here, this is clockwise. Can see? This is my pivot. My weight is going this way. A very good way to visualize this is this pivot here, this way. Clockwise. How much is my clockwise? My clockwise is F times D. Clockwise equals to anti-clockwise. Don't worry, we'll do it step by step. My clockwise here is 20 times 2. My anti-clockwise is F2 times 5. The value of F2 is 8. You could hypothetically let F2 be the pivot to solve for F1 as well. There isn't a strict rule here. You let either force be the pivot. You want to be physics god? Let me teach you a bit more. Okay. So this entire thing is in equilibrium. Upward force equals to downward force. The downward force is the weight. Weight is 20 Newton. So if this guy here is 8 Newton, down is 20. Make a guess, how much is F1? 12. These two go up, 12, 8, upwards. Weight down 20. Cancel each other out. Upward force equals to downward force. So the relationship between F1 and F2 is that F1 is bigger by 1.5 times of F2. So the answer here is 8. 2 of F1 means 2 times 12 equals to 3 times 8. Hey, y'all don't blame me. Y'all say you want me to go through and then I just go through, okay? But I admit it's quite hard. So if you don't fully get it, it's fine. This one, don't sweat it. I feel like your school won't set for end of year. Okay, it's fine. This is more like a Sec 4 kind of question. So quite difficult, but good to go through. So in summary, if you don't have pivot, you can let either force be the pivot. You solve first using clockwise and anti-clockwise. Once you're done, you can solve using upward equals to downward. Okay, so that is for question 2. Let's move on to question 3, final one. So here we were told that the toy is being pivoted on a triangular stand. So even when we tilt the toy slightly, it remains stationary at its new position, which means the toy, I can keep turning it and it still stays there. Wow, magic. How does it work? As long as the center of gravity is passing through the base area, it would stay in stable equilibrium. So I know a lot of you will go like, sure, this is the toy. My center of gravity must be here, here, or here, right? Doesn't have to be the case. The center of gravity, look at the hand. The hand is low, right? So as much as you have your body with your arm, if this two ball, right, is super duper heavy, it's totally possible for the center of gravity not to be in the body region, but here. And the reason why this keeps it in a stable equilibrium is because this dot doesn't move when the body moves. The center of gravity still stays within the base area. So stable. Okay, this one is a bit hard to understand. I know this is a more unique example. Not the typical kind that you always see, like the bus, and then will fall or not. Yeah, those are quite easy. But this one really is about making sure that you understand that center of gravity doesn't always have to be inside the object. It can be outside the object. I give you a simple one, a donut with the center in the middle. Where's the center of gravity? It's in the middle. You get what I mean? So it doesn't mean like I have my object. Doesn't mean my center of gravity has to be in the part with the bread. My center of gravity is here. So the point I'm trying to make is center of gravity is where the weight appears to act on. It doesn't have to be inside the object. But you get the donut example. It's not that complex, right? So I'm mainly trying to communicate with you the idea that center of gravity can be anywhere. It doesn't have to be inside the object. It can be outside. So this entire thing is my toy. But my center of gravity can be here. Possible. That's all. The question will change. Okay, it won't be exactly this question, but the understanding needs to be opened up. Okay, you don't limit the thought of what you think of center of gravity. Okay, let's move on to pressure. Yeah, no pressure looks like a lot of formula. It's pretty tough, but don't worry because specifically for Sec 3 end of year, they usually test the same few question type. So I'm going to focus a bit more on going through the same few questions that usually come up. Now, the one that I can say confidently you guys know is force over area. That one you don't ask me to go through. I'm not going to go through. Okay? But I want to talk about liquid pressure, barometer, manometer. Those are usually I don't get it kind of thing. Okay, so I'm going to go over to the notes here. First, I like to use this one because it tells you a very clear picture. Understand this, pressure. Wait, lagging. Pressure is force over area. But to find liquid pressure, we do rho GH. Rho is density. It's pronounced as rho. Don't ask me why. I also do not know why. It's just called rho. Okay, density of water, gravity, height of liquid. What is really important for us to understand is that the container can come in all shapes, sizes, even slanted. I don't care about any of that. I only care about the height of the liquid. So you notice here for A, B, C, D, all of their height is the same. In other words, the water pressure is exactly the same. So you throw away everything that can confuse you. It honestly doesn't matter what you are dealing with. As long as the height is the same pressure. More height, more pressure. Lesser height, lesser pressure. There's a more in-depth explanation, but a bit too complex for me to go through now. I hope you can understand. I only have 15 minutes. But the main point I'm trying to make is that for liquid pressure, we only care about the height of the liquid. If you can bear that in mind for your end of year, you'll be safe. Okay, so I give you an example. I like this example a lot. We can use this as a basis to compare A and B. Do you all agree with me that the height is exactly the same? So what is the pressure? Pressure is the same. That's it. You don't have to think too hard. I know A has a larger area, but it also has more water. So it has more weight, larger force, larger area. The bigger B, smaller area, but also lesser water, so lesser weight. So smaller force, smaller area. So big force, big area, small force, small area. The pressure is the same. How do we know it will be the same? It's just the height. That's it. So you are literally just using height to determine liquid pressure. Full stop. You don't overcomplicate things for yourself. The question will try to screw you over in different ways. They'll give you, wow, beautiful container, the things like whatever. Okay, no vertical height, that's all I got. Okay, everything else, those are all distractions. So the vertical height is how you calculate liquid pressure. Next, the other one that will come out, this is the one that we predict will come out for end of year, hydraulic press. The two formulas that I believe are more important is this one and this one. Later, we'll go through a question on it. Okay, these two, I'll prioritize it. Basically, pressure throughout is the same. Work done throughout is the same. But this one, don't worry too much because later we do a question together. The question will help you understand it a bit better. Anyway, if you are studying for your end of year, don't be naive to say, I just flip textbook, read my notes, memorize formula. It doesn't work. You have to do a bit of practices. If you can't apply the concepts, it's as good as not knowing the concepts. Okay, so you do need to do your workbook, or if you want your topical TYS, is a good place to start. Because O-level questions are actually not that hard compared to our, say, prelim questions. You all shouldn't be touching prelim papers yet. Unless it's a Sec 3 end of year paper, then quite realistic. Okay, now, what else do we need to know? We need to know about your mercury barometer. I feel like you all recognize the diagram, but I bet you all don't know how it works. True? You're like, yeah, I get it. It's a mercury barometer, but like, how does it work? Actually, it's not that hard. Okay, so around us, right, there's air. Air, the molecules anyhow fly. So the molecules slam into a surface, it exerts a force. We call that force over area, atmospheric pressure. Atmosphere is just air. So the air around us exerts a pressure on any surface that's exposed to air. So right now, you and me, we're sitting here, we are experiencing atmospheric pressure. Is it that like we're so used to it, we don't really sense it? Yeah, but it's a thing, it's a real thing. So air does bombard against any exposed surface, they do exert a pressure. We call that atmospheric pressure. But how is that relevant to a mercury barometer? The entire basin here on the surface, these portions here that I'm highlighting in yellow, they are exposed to air. So the air molecules are bombarding against these surfaces. So this one here is atmospheric pressure pressing down on the basin. So imagine an invisible hand, okay? The basin are pushing down on it. So when I'm pushing down on it, what will happen to the mercury? The mercury has nowhere to go, right, but to zoom up into your test tube. So that's how the mercury goes inside the test tube, because there's this like invisible air pushing down on the basin. Like I press down, then I force everything to go inside the test tube. So what is in your test tube is the equivalent of your atmospheric pressure. So this thing, the 76 cm millimeters, this one represents your atmospheric pressure. Now, how exactly does it work? Mercury in periodic table, if you go and check, the symbol is Hg. So we like to write 760 mmHg. This one here is not that hard. This is just liquid pressure, rho GH. To calculate, if we wanted to, we could have taken the density of mercury. This is, you do not need to know the number. I just happen to know it, okay? But ignore me. They will usually give you in the question. G is what value? Then, what is the height? 760 long. But we don't do it in mm. What's the SI unit for length? Meter, not centimeter. So 0.76 meter. So that is equivalent to 760 mmHg is just a way to display the pressure. You can calculate it as liquid pressure as well. It's totally possible. Okay. Hard, but I'm trying to get the key points. If I have a full 2 hours, believe me, this is going to be super easy. I have 15 minutes. I have to be selective with my time. But at the end of the day, I hope at least you all understand how the mercury basin works. We press down on it, the mercury zoom out long. That column is atmospheric pressure. It tells you how much atmospheric pressure is. Okay, in the notes, I also taken some time to include the situations that happen. If you replace it with water, if you tube the glass tube, what will happen, right? So all of this can be an exam question, 1 mark. Or if I use water, what's it? If I bring it to higher altitude, what is it, right? So all of this you can go and study. So let's take a look at question 1. This is the hydraulic press. I want you all to take a minute properly to read through the answer in part A. This is important. This is understanding how your hydraulic press works. It's all English, so you should understand. So the main thing is that when you have a hydraulic fluid, it is enclosed within the entire system. It cannot be compressed. That's number one. Secondly, pressure throughout will be equal. So whatever pressure that piston X experiences is the same pressure that piston Y experiences. Pressure, same. The godly formula that you will need to bring into exam is F1 A1, F2 A2. This formula, you can find it inside your worksheet/notes, is what we are talking about over here. Small force, small area, large force, large area. So this one, if your school is kind, actually if they set it, it is to your advantage because this is a lot easier than a barometer or manometer. So usually at Sec 3 end of year, they will test you on this. The calculations are also quite straightforward. But the formula, this one you need to know. But if I simplify the formula, it's just saying that the pressure on both sides is the same because force over area is the same. So don't overcomplicate it. This is how you should think about it. Yeah, whatever you learn today, you still need to spend maybe another 1 hour on your own to look through again. So for you to truly absorb, because a lot of these concepts are a bit harder. Okay, last 20 seconds for those who are still copying. Don't stress, got answer key. Okay, so if you're not copy finish, it's fine. But I mean, it's a good thing that you are taking it down. Okay, the ones that you will be a lot more concerned with is how to do the calculations. So for part B, right, is using the formula literally F1 over A1, F2 over A2. I'm not going to bother to do the math part. You'll get it. You will eventually solve for F. I think part C is where it gets slightly more challenging in this sense. The formula to use is F1, D1, F2, D2. Do you know what's F times D? Work done. In other words, work done on both sides is the same. Later, we'll talk a little bit more about work done in the final chapter, right? But these are the two formulas you will need to know to do questions related to the hydraulic press. This one must know. This one must know as well. There's a third one, but that one I think don't need to know. That one is like extra, like you're a bit hardcore, then you go and you know that volume is the same, but no, these two is more than enough. Okay, let's move on. Final chapter. You actually give it to normally people are usually dying already. Final chapter, okay, we put it through. Last chapter, work, energy, power. Okay, then we do out the question, then we finish up today. Like I told you, it was supposed to be intense. I love it that way. Okay, come. Big picture, big picture. Before I go into our formula, all the other nonsense, work, energy, power. What is the relationship between energy and work done? We use energy to get work done. Let that sink in. We use energy to get work done. I'm telling you this, Energy and work done is the same thing. What's the unit for energy? Joules. What's the energy for work done? Technically, joules as well. Same. That is one of like the biggest hurdle at Sec 3 that you're like, wait, what? That didn't sink in my head. Let it sit in. Energy and work done is the same thing. So in other words, later on when I do certain questions, when I gain energy, that's work done. When, for example, if I move faster, it's considered work done because I gain KE. I know it feels a little complex. When we do the question, maybe you absorb it a bit better. But this is a fact, all right? That energy and work done is the same thing. Later, I'll explore certain specific questions to help you understand this a bit better. Now, the one that I believe you guys are good with is half mv square mgh. That one, don't waste time. Can? KE, GPE. That one, I think you are fine. Where I'm worried about is the work done part. Okay, so I'm going to use a specific example to illustrate how work done and energy is related in the bigger picture. My favorite one is this one. Okay, you want to copy down, can, take photo, can, I don't really care. I just want you all to understand this. That's most important. So I'm going to move this box from point A to point B. Okay. What I think we are quite comfortable with is that we can go like, okay, sure, I know this one, right? F times D. Right, work done. If I need to move the box from point A to point B, force times distance will give me work done. This is true. This is true. So formula-wise, I have no doubt most of you are somewhat comfortable with work done equals to F times D. But that is a very basic understanding. It won't get you far. B3 is possible, but you want to get an A1 in Sec 4? Near impossible. Let me go into detail on how you should be thinking about work done. Work done is, in total, the journey from point A to point B. What needs to be accomplished to get from A to B? There are two main things we need to settle. If I have a human being pushing the box, this human being needs to do two things. Firstly, the journey from A to B, there is friction. There is what we call work done against friction. I need to exert a certain amount of energy to overcome the friction. If I can't, my box will move already. You know, sometimes when you move stuff, cannot move, cause too much friction. But if I have enough energy to push it, that I can overcome friction, then my box will move. So the first thing we are considering is the work done against the friction. The distance moved is 5 meters. The friction is 3 Newton. Work done against friction is 15 joules. As a human being, I need to burn 15 joules to overcome the friction for the whole journey. This is work done against friction. Not work done, work done against friction. To move the box from A to B, on top of overcoming friction, we still have to increase the GPE of the box. What do I mean? Energy cannot be created nor destroyed. Energy doesn't miraculously increase when I move from A to B, right? A to B increase GPE, right? That one I think you'll get it. But did this GPE suddenly materialize out of nowhere? Cannot be. Somebody was responsible for increasing the GPE. Who is it? The poor human here. So the poor human has to increase the GPE, and that would be about 30 joules. In other words, if I say what is my total work done, my total work done is actually work done against friction plus gain in GP. So the whole journey, there's two main components to it. To get me from point A to point B, I need to first overcome friction. Plus, I need to increase my GP. If I add these two up, that's my total work done. I'm going to drop in some numbers, okay? Hopefully that will make it a bit clearer. What is my work done against friction? 3 Newton over 5 meters, 15 joules. To increase my GPE, my MGH, 30 joules. What's my total work done? 45 joules. Now, it is true that work done is F times D. What's the distance that I move by? 5 meters. So as a human being, how much force do I exert pushing the box up? Is it more than the friction? It has to be. Because on top of overcoming friction, I need to push enough that I can move it to increase the GPE. So the total work done is one big ball. Part of it is used to overcome friction. Part of it is dedicated to increasing the GP. So that is what we call total work done. It's not so straightforward, F times D. You think about F times D, no, not so easy, right? It's the same thing as RF equals to MA, if you get what I mean. So I'm really just trying to open up the way you look at physics. There are questions that will, actually, this is not considered that difficult. This is quite typical at Sec 4. I know now at Sec 3, maybe you haven't yet full, but this is quite a normal O-level question. Okay, so listen up, energy and work done is the same thing. When you move something from point A to point B, you need to overcome friction plus increase the energy. That is your total work done. You can actually find this in the notes over here, illustrated in this point. Okay, but I think my explanation is a bit better, so I use my explanation, but you'll get it most important. Okay, principles of conservation of energy, whatever, you're just going to read by yourself. This one is English, you get it. Okay, so my main takeaway is work done. Don't be simplistic. Okay, it's not that straightforward. Okay, it's not just about the formula. This one is one of the more crazy questions, but I think there's a lot of value because I'm going through if you're not doing it by yourself. So I want to take you through this step by step. When we fire a bullet or a pellet and it hits into a plastic block, you can visualize, right? The block will swing backwards a bit because there's like an impact. So let's take a look at this in terms of numbers, in terms of work energy power. How to calculate the KE? Don't waste time, half mv squared. This one shouldn't be a problem. If anything, can I just get you all to promise me this? What is the careless mistake you'll be making in exam? 25 grams, just write down, right? But what's the SI unit of kg? For my own Sec 4s that are taking O-level soon, they don't dare to tell me careless. Why? Because I already warned them of all the places where the careless mistake will happen. So this is just one of them. So if you're very conscious that, okay, there could be a tricky part, they will leave it in gram. But I know I'm supposed to leave it in kg. There's no such thing as careless. You're supposed to be aware of it. Okay, so remember, mass should always be in kg. Sometimes the height, they will leave it in cm. You must convert to meters. Those are all things you need to build. Good habits to build early. So half mv squared, no problem. Now, the next one, the pellet comes to a stop. Calculate the force. Now, to calculate the force, F equals to ma. The mass of the pellet, same thing, 0.025 kg. You would find the deceleration, technically. So it used to come in at 60. When it stopped, it's at 0. So acceleration can be found by taking the difference in the speed of acceleration. That is how you find the force itself. And how to calculate work done? Force times distance, right? So over here, we simply take the 75 times 0.015. Okay, before I go on to part D, in case you haven't realized that this is a thing, the chapter for work energy power is freaking annoying because it can bring in all of your previous chapters if it wants to, right? Because F times D, how to find F? F equals to MA. How to find A? A is equals to V minus U over T. So you get what I mean, that you cannot just think of it as chapter. They are all linked. Acceleration is linked to F equals to MA. Force is linked to F times T. So that's why we have to look at the entire mechanics as like one big chapter rather than a fragmented one. So I think example A, B, C illustrates that quite well. Okay, then you can find force first, then you go and find your work done. Okay, so what is the theoretical maximum gain in GPE? Just remember that energy cannot be created nor destroyed. Initially, our energy we have already found in part A. This is the 45 joules. Your final energy is GPE, but where did this 1.125 come from? Anybody can tell me? Is your work done against the resistive force? Now, whoa. Sure, what are you talking about? So the bullet got KE. That is the amount of energy I start off with. When I slam into the plastic block and I slow down, understand that there is work done to slow it down. That is what we have calculated in part C. Remember at the start of the chapter, I said something? Energy and work done is the same thing. So here, if there is a 1.125 joules that is used to slow down the pellet, maybe due to friction or something, I need to subtract that away. Because energy cannot be created. I started with 45, my total amount will be 45. But maybe out of this 45, 43.9 converted to GPE, while 1.13, it is quite similar to the slope example just now, right? My total work done is friction plus gain in GPE. Here, the friction is technically 1.13. The gain in GPE is the remainder of the 45. 45 is total. This total, I need to split it up. A bit used to overcome friction, the rest turn into GP. So that's why the box will swing up, but it will not be 100% transfer. So it's not KE to GP straight away. There's a component where it's work done against friction. The energy type is usually heat. That means here, 1.13 turn into heat, the rest turn into GP. So KE converted to GPE plus heat. Be exam smart, whatever you calculated in part A, B, C, D are related. So if you are stuck, how to do D, go and look back at the previous part. They will be somewhat relevant to whatever you're doing. So that is another way you can troubleshoot yourself in an exam. All right. Finally, once you have GPE, you can calculate using the formula to work backwards to find the height. Part E is easy. Part E, no problem. You'll get it. Just don't get your units wrong. But there is one very cute part. I think this one is like a bit like, wow, they a bit asshole, but you know why? Because now, right, do we only take the mass of the plastic? No, right? We have to do the plastic plus the freaking pellet that's stuck inside. You get what I mean? The bullet that's stuck inside. So that's the total mass. So a lot of us will just take the plastic block, we just take the 8 kg. But no, we still need to add that tiny little pellet that's stuck inside. So that's why there's a plus 0.025. Yeah, so unit for energy will all be in joules. As much as the formula is half mv squared or mgh, the final formula that you derive out of it is still joules. Okay, whether you believe it or not, we covered 6 chapters in 2 hours. Intense, I think it's quite intense. All right, and I feel like a lot of the questions that I went through, maybe you understood about 50 to 60%, but I hope that those key emphases are clear. So today is not a chance for me to like really go through concept by concept, go through a few of the same question type. I don't have the luxury of that. But I think what I was more focused on is to open you in terms of the perspective of things that you might not have thought about. Things like RF equals to MA. Right? Things like, in this case, energy and work done, the broader concept or how the barometer works. Those will stay with you well. Then when you do more practices, you will naturally get better at it. So I think that has to be the approach when you are learning physics. Okay, I think there's not much else for me. So I really hope that you guys learned something today. Of course, it will be good if you can review after today, right? Go and learn about some of the stuff. Beyond that, there's not much else. I know some of you might be thinking, oh, wow, after end of year, my results, so do I want to join tuition? Up to you. We don't force you, only if you need it. But just to share with you some of the timeline, if you sign up in September, it's a bit better. There's a lot of like free stuff because it's like early bird shit. But if you don't want, you want to wait until after end of year, your result come out, that's perfectly fine as well. Because maybe you don't need tuition, okay? But we will be having free trial lessons for you to sign up in October. Free trial is legit like free like today . So you come now, you sit in for a lesson. If you want to, then the lesson will start in late November. So this is largely for the Sec 3s going to Sec 4. It's about a 12-month program from the time you start to the time you take O-level. But this one, I say you all go and take your end of year first. Then you all decide if you need it. But if you want to sign up early, there's a lot of free shit, so might be good. Hey, that's all. We did it. If you all don't mind, can you just help me scan? It's a very simple survey. So we're just trying to explore the next time when we do this, how we can make it better. So no name, anything one. It's just like you just feedback. Actually, I don't know whether there's a name or whatever, but just help me fill out the form. It will be quite helpful. Okay, if you have any burning questions, you can stay back after class. I can still go through with you a little bit. For those of you who are coming back for more sessions, you'll be here lah. You all know how it works already lah. Okay. Feel free to loot the goodie bag, but if there's extra tote bag, you can leave it around. That's all. Those that came a bit later, right? You all know the shelf outside, there's the revision kits. Go and take for the subjects you want. So go and take. You can take 1 or 2 for your friend too. It's fine. We printed enough for everyone. Right.